Hi guys, this is a video on the big five time complexities in data structures. It turns out that there's only five big O efficiency classes that tend to come up in a data structures course like this. It's true that the big O classes are open-ended. You're allowed to put any math function in terms of n in between the parentheses there. So you could have things like big O of n to the 3/4 time and things like that. But in practice, data structure operations almost all fit into one of these first three. These have names because they're used so often. Big O of 1 is constant, big O of log n is logarithmic, big O of n is linear. And of this list of five, all of them are usually considered scalable except for big O of n squared. N squared, which is called quadratic, usually does not scale well enough to be practical. So it turns out actually that almost every data structure operation is either big O of 1 or big O of n. That's true for the first part of our course. The whole time that we're talking about arrays, vectors, linked lists, stacks, and queues, every operation is going to be either big O of 1 or big O of n. And for those data structures, our analysis really boils down to just deciding, is this a big O of 1 or a big O of n operation? As we'll see, balanced tree operations have this somewhat unusual big O of log n runtime, which is a little bit different. We'll see why that is. It has to do with how balanced trees work. Big O of n log n is derived from log n. It's just a big O of log n operation repeated a linear number of times. Similarly, n squared, big O n squared comes from a big O of n operation repeated big O of n times. And that's the only non-scalable class on the list again. Now we're going to go through each of those five in a little bit more detail. First, big O of 1. This is pronounced constant time. In a big O of 1 constant time operation, the amount of time spent is unrelated to n, the input size. So that's perfect scalability. No matter how big the input is, the operation takes about the same amount of time. This is the best efficiency class, and if we had our choice, every data structure operation would be big O of 1. That's not actually possible for some technical reasons that we will explore. This graph shows a picture of what this relationship looks like, and I'm going to have a graph like this for each of the five, so I want to highlight what's going on here. On the horizontal axis, we have the input size. This is the number of inputs, or in the context of data structures, the number of elements in the structure. On the vertical axis, we have the time. This is the amount of time it takes to do one of these operations as the structure gets bigger and bigger. And this being a constant function, it's a horizontal line, meaning that the amount of time does not really increase as the structure grows. Big O of n is the other commonly encountered alternative for most data structure operations. We call it linear time because it represents a linear relationship. The amount of time spent is proportional to n. So as the structure gets bigger, the operations take more and more time in a linear proportion. This is ordinarily considered scalable to do as an individual operation. Here's what that would look like as a graph. So we have a straight line with a slope, a positive slope. Big O of log n involves logarithms. It's called logarithmic time. And it does grow. It is a growing function, but it grows a lot slower than a linear function n. So it slots in between big O of 1 and big O of n. A log n operation is slower than constant, but faster than linear. And in practice, it's really close to big O of 1. Log is such a slow growing function that for most practical data structures, the amount of time is so close to constant that it's almost the same thing. So this is also a very desirable runtime. It's not quite as fast as big O of 1, but it's still very efficient. And ordinarily, this is considered a scalable operation. Here's a plot of what that looks like. So you can see that this is growing as the input size increases as we move to the right. The time on the vertical axis does go up, but the rate of increase gets slower and slower. And as the data structure gets very large, it kind of tapers off and doesn't really slow down very much. That's why this is a very fast, scalable runtime. Big O of n log n for us is derived from doing a log n operation from the previous graph n times. It's just pronounced n log n time. We don't have a nice name for it. Maybe you could think of a nice name for this. N log n does grow. It's n multiplied by log n. Both of those are growing expressions. So this does grow, but a little faster than big O of n, but not a lot faster than big O of n. And it's close to big O of n in practice. Just like big O of log n is close to big O of 1, big O of n log n is pretty close to big O of n in practice. And this is normally considered a scalable operation to perform. Here's what this looks like when plotted. Again, I have input size n on the horizontal, time on the vertical, and this looks like a growing function, and subtly it's growing a little faster than a straight line. It's not quite a straight line, it's pulling up a little faster than that. So it does grow faster and faster, but only a little bit more than linear. Finally, big O of n squared. This is pronounced quadratic time because it's a quadratic polynomial. This runtime grows faster and faster and is ordinarily not scalable because it grows pretty fast. And this is something that then usually needs to be sped up. If we have an operation that takes quadratic time, we need to do our best to try to speed it up. What's going on here usually is you have n big O of n operations that are repeated, and we want to replace that with n constant time or n logarithmic time operations to get a better runtime. Here's what this looks like. It's a parabola, and it does grow faster and faster. As n gets big, you might notice that the time units here are quite a bit larger than they were in the other examples. They're on the order of millions. Here's the big five compared. What you can see on the left graph is all five of them. And because n squared grows so fast, it's the line in orange, it goes kind of off the charts here, and the other four just appear all on top of each other. They're growing so much slower than big O of n squared that they look indistinguishable. So to focus a little bit more on the ones that are close to each other, on the right I have the first four, not including big O of n squared, as they grow as a function of n. And what you can see in green is n log n. It's the fastest growing, so that would be the slowest operation to run. Big O of n is in yellow. It comes in second. And then the others, big O of log n and big O of 1, are on top of each other here. They're indistinguishable in this graph. So as I said, big O of 1 and log n in practice are pretty close. This tells us how data structures can help. We have this really common kind of loop. This is a very practical thing in software development. You have a loop that repeats for each element, and it does something. And if that something that it does is a naive linear time operation, then we have n repetitions of a linear operation that makes n squared time or quadratic time, and that's not scalable. This would be too slow to involve in an app that deals with any kind of volume of data. So what we often need to do is replace this naive big O of n step with a constant time data structure operation, using one of the data structures we will learn about the way that they're meant to be used. Then this whole loop becomes n constant time operations. That multiplication gives us big O of n time, and that's scalable. Or, similarly, if we replace the linear time operation with a log n time operation using a balanced tree, it would become big O of n log n, and that's also scalable. So this is a very practical skill. It's one of the big points of a course like this. This is something I myself have done in practical software development many times, is identify one of these quadratic loops and then use a off-the-shelf, well-defined data structure to speed up the body of the loop to go from a non-scalable quadratic time to a scalable linear or n log n time.